In this video, I wanted to discuss how do you simplify trigonometric expressions, and then how do you use that idea to verify new identities. But one of the ways I'd like to think about it is thinking about a lot of those identities that I reviewed in the last video as kind of our fundamental building blocks of the rest of building new identities. So basically, they're like various different rules or formulas that we can use to do new things. And kind of remembering these really reciprocal and Pythagorean are the kind of the most common building blocks that you want to be using in these identities. But basically, applying these rules and using them to simplify other expressions. Like for example, it says to simplify these things. Cotangent theta, secant theta divided by sine theta. But upon initial inspection, these expressions can seem quite daunting because I have a bunch of different trigonometric functions all jammed together. And if we start trying to think about, well, what does all this mean? It's enough to make our head spin because each one of these is a different component upon the unit circle, and there's a lot of various different ways of looking at this. But essentially, the idea of simplifying is to kind of try to use algebra to make these look better. And one common theme or suggestion for a strategy is to, if I'm dealing with a whole bunch of different trig functions, it's sometimes helpful to turn them all into sines and cosines because really each trigonometric function, as the reciprocal identities suggest, could be changed to terms of sine and cosine because that's really I think I talked about this earlier. Really, there's sine and cosine x and y. Each other trig function is just a ratio y to x, x to y, 1 to x, or 1 to y. So they're all kind of similar at the end of the day, and that's kind of the idea for these. We could try to put these all into the same terms, or as I might say it, change them to sines and cosines and see, well, what does that suggest about the expression itself? But basically, if I take each part of this, cotangent is x over y by fundamental definition, which is cosine over sine. And basically, this theta doesn't matter what it is, but notice that it is the same in every function, which is imperative in terms of simplifying these. If they're not the same, it's not going to work this way. But basically, the cotangent is always equal to cosine over sine of the input, or sometimes theta is referred to the argument. What is the input value of my function? Um, just the variable theta in this case. Secant also, well, that's the reciprocal to cosine 1 over x, or 1 over cosine of theta. So if I kind of change secant to using its reciprocal identity, and then sine is already in terms of sine and cosine. So this kind of makes things simpler. Now everything is in terms of sine and cosine. And if I notice on the top of this expression, I have cosine divided by sine times 1 over cosine. Well, if I was to write that a little differently, really what I have is when I multiply fractions, what will happen is I get top times top divided by bottom times bottom. So what I would notice about that is, well, that would just make 1 times cosine on top divided by sine times cosine on bottom. And that's all divided by another sine, which I don't want to forget. But the numerator of the larger fraction will multiply into this, which of course has a common factor of cosine, which would indeed cancel, because if you ever have the same thing divided by itself, that will make 1. And what this would leave me with is 1 divided by sine over sine. And you might be tempted to cancel out sine over sine here, as I did right in the step before, but be very, very careful when you cancel because this is actually not the proper situation for cancellation of those signs. Because I don't have sine over sine, I have 1 over sine over sine, and that actually does not cancel. Because if I think about, again, fraction math, right? If I take a fraction and I divide it by a non-fraction, well, I could write this as a fraction over 1. Really, a fraction divided by a fraction, I should flip and multiply this. So notice that we're using a lot of basic algebra rules, right? Rules of fractions and so on. And those, all your previous knowledge of algebra and stuff is going to be really critical here, which is why I'm reviewing it now. And if you're ever stuck on something, please ask, because I've taught all the most basic, levels of algebra and fractions and whatnot. And all those rules are not necessarily obvious. So a lot of times I get students who think I should know all this, and really, it makes sense that you don't remember everything. So I'm happy to always go over anything, never feel like it's too easy, of a question to ask me. But anyways, what we would get is 1 over sine, flip and multiply by 1 over sine, right? Because if I'm dividing by a fraction, that would be the same as flip and multiply. So really what I'd end up with is 1 over sine squared theta here, which technically we could also clean up, because if I think about a fraction of squares, I could also write this as, well, this is 1 over sine quantity squared, because if I square a fraction, it would square the top and bottom, which would leave me with 1 squared 1 over sine squared sine squared. And my whole point in this is that, well, what I end up with is 1 over sine squared. Well, 1 over sine squared, 1 over sine is actually equal to the cosecant function. So if I'm really trying to simplify this as far as possible, I could write this without the fraction just directly as the cosecant function of theta squared. Because that's what I have, right? This is cosecant, 1 over sine squared. But after all is said and done, this is the point of knowing all these identities. I can take a pretty horrible looking expression and try to simplify it as much as possible. And after all is said and done, I can conclude that this giant thing is actually just as simple as a cosecant square function, or 1 over sine squared function. And in so doing, we're making our life easier by really taking away all of the complexity and turning it into just one single function. And if you're wondering, well, what is the right answer here? Because there's no such thing as a correct answer. Really, it's just an alternative form of the same expression. Like, really, this 1 over sine squared is another pretty fine answer, because just using sine is a lot of times better, or cosecant squared. So there's not necessarily a right answer, and that's why this is kind of different than a lot of other math. It's like, where do I stop, or how do I know when I'm done? It's kind of contextual. It's really all about understanding how to change one type of expression to another, and really we're going to be using all of these rules in ways that would make sense. So kind of the point of a lot of these videos is to help you see when they're useful, and like situationally which ones, strategically, which ones would I want to apply. And let's look at a couple more. So say, for example, I had sine A minus sine of negative A. Well, anytime you see a negative within a trigonometric function, that's where I would naturally go to the even odd identities, because those basically tell me, well, what happens if I have a negative? What will become of that? And in the case of sine of negative x is always equal to negative sine x. Or another way you could think about that, as the negative within a sine can pass through the sine. So like, say I have a negative here and I want to know how to deal. I could basically pull that negative out here instead. That should be fine. So in the case of this question, well, sine of A minus the negative would pull out front. It would be minus a negative sine A by the odd identity for sine. And of course, well, I have minus a negative. Two wrongs make a right in math is the joke. But basically that would leave me with sine A plus sine A, because I have minus a negative, which turns to plus. So it's like this negative will multiply into the other negative and just change to a plus. That's fine. And notice that this would work differently with cosine, because cosine is not odd, cosine is even. So it just depends on the function, but some functions work quite simply. And also from here, if you're wondering, well, how do I add up sine plus sine? This is something we haven't really done before in our class, but it's kind of like, a lot of times we have an algebraic identity, like I was saying in the last video, x plus x is equal to x. Sorry, x plus x is equal to 2x. Because if I have something and add exactly the same thing, that's always equal to twice the thing, because just by basic principle. And that can actually be applied sometimes in trigonometric expressions as well. And sometimes this might not be obvious, but if we think about it, sine of A, we don't know A, so we don't know what it is. But if I want to add exactly the same thing, sine A plus itself, well, that's going to make two of those things, 2 sine A. That's not a trigonometric identity, that's just a basic algebraic identity. But what we end up with is a simpler expression, and we're kind of trying to combine all of these into one if we can. Like over here, we took all three of those things and made them into one trigonometric function. Here, same sort of deal. We're trying to combine them, join them together, simplify it in any way that we can. And once we get, the question is when do we stop? But at a point where we think, well, we can't really go any further, that's when I would usually suggest saying, okay, this is my answer. And say, for example, with 1 over cotangent x squared plus 1, one way we could deal with, again, like anytime I'm dealing with cotangent, cosecant, secant, and tangent, we could always try to change them to sines and cosines and see what happens. But with cotangent, cotangent is equal to cosine over sine, or it's equal to the reciprocal of tangent. I could use either one of these if I wanted to. Technically, you could use any identity you want, but be careful about using it. Make sure that it makes sense and you're not misusing the particular identity. But in the case of cotangent, cotangent is reciprocal with tangent. So actually, logically speaking, 1 over cotangent goes back to just tangent. But, algebraically, I wanted to show you, why this makes sense and kind of say this is a general property you can use without having to do any math. But the cotangent is equal to 1 over tangent. So cotangent squared would also make sense to be 1 over tan squared. So again, kind of like what I'm doing is I'm taking, sorry if it's a little hard to follow me sometimes, I'm taking this and I'm rewriting it using one of the things that I saw above. So, well, what is cotangent x? It's equal to 1 over tangent x. Cool. And since it's squared, well, if I took this side and squared it, it would also square this side. So what that would leave me is 1 over tan squared. Naturally, these properties work for squares and cubes and powers as well. But anyways, what you see is that I have a double reciprocal 1 divided by tangent. And by flip and multiply rule here, again, trying to deal with such things, I would use the rules of fractions because I have a non-fraction divided by a fraction. And if I divide by a fraction, that would leave me with 1 times reciprocal of the bottom. So basically, flip and multiply, that would become tan squared over 1, and really have 1 times tan over 1, which is, of course, just tan squared x. And then once I have tan squared x plus 1, the last thing I could notice here is, well, that's equal to secant squared of theta by Pythagorean identity number 2. And so I can, in this case, simplify that expression down to a form where I can get into just one trigonometric function, take something rather horrible, and make it simpler. That's kind of the idea. In the next video, we'll talk about verifying trigonometric identities. So there's a specific set of guidelines I wanted to discuss, and then kind of get into some examples of harder identities. How do we prove these things are true, or how could we show something to be false?